About the review. Okay, so let me pull up the review sheet. Oh, might help if I turn them on, the projection on. Now, I don't know how many people noticed, I did slightly update the review sheet yesterday. Very slight changes. I added a couple of topics that we had covered in class that wasn't on the review sheet. People were going, wait, do I have to know about this? Yes, you do. It's on the review sheet now. So if you don't have the most current copy, feel free to jot that in, or just push it up later. It's not really a big change. All right, you had questions? General question about the exam?
For the fatty acid.
Yes.
Are you going to give us the
Length, and then yes, for this exam, and for the accounting of fatty acids, I am going to give you the length and where the double bonds are. Yes. Not just the name. That's for the final. Because on the final, you have to memorize everything you did. So, since I'm not making you memorize them for this exam, you get a break. But for the final, you have to have memorized them for the whole thing anyway. So why not? Very good. All right. Let's go through the different topics. It's actually still 2 pages, so it's not any longer. Don't worry. Basically, we started with lipid metabolism. The fatty acids, there was beta oxidation. Now, I'm not going to make you reproduce the steps going to the transient oil or the hydroxyl. I'm not going to make you draw those. But you do need to know what steps are there. Like you get an NADH and an FADH, and then you produce an acetyl-CoA. So essentially, this is the accounting right here. The FADH, the NADH, and the number of acetyl-CoAs, and how you calculate those. And then accounting for unsaturated fatty acids. Odds reduce our yield by 2 ATP, and evens reduce our yield by 3 ATPs. And this is done, as somebody asked, they're done as the beta oxidation system approaches that double bond, then it changes it. So it doesn't automatically change it in advance. But the overall accounting, we're just going to add them up at the end. All right, any questions about that? We're good on that? All right, and you will have definitely accounting problems, just like you had in the last exam. Ketone bodies, the 2 that I mentioned were acetoacetate and beta-hydroxybutyrate. Know how much energy each of those is worth. I wrote that on the board. 24 for acetyl-CoA, 27 for beta-hydroxybutyrate. Okay? Then we went into fatty acid synthesis, which was essentially oxidation in reverse with 4 main differences. Know your comparisons. I'd ask you to write those comparisons. That's a big hint. Okay? The location, oxidation is in the mitochondria, beta synthesis is in the cytoplasm. Electron carriers, whereas oxidation uses NADH and FADH, synthesis always uses NADPH. Your acyl carrier is coenzyme A for oxidation, acyl carrier protein for synthesis, and the carbon unit is acetyl-CoA versus malonyl-CoA. Remember, malonyl-CoA is the higher energy molecule. I added a carbon dioxide to make it higher energy so that I could favorably add carbons instead of subtracting. So it's easy to cut the carbons off. I got to pump a little extra energy in to add them back onto the carbon chain.
And with structure, it's just the 2 hydroxyl?
What is
The
what?
structure between malonyl and...
It just has a carboxylic acid. That's all. The only difference is you take acetyl-CoA and you add a carboxylic acid onto that far end. That's what's added and subtracted later. Longases and desaturases, I went through how those worked after C16. And do expect the part 2 problem like you had on the practice problems. Everybody comfortable with those? It seemed to go pretty smoothly. I didn't have a lot of people. Yeah, you can both put this up. When you were stopping C16. Yeah, you always stop. Just like on the practice problems, I say, starting with C16, how do we get this? And you work your way all the way back to C16. So even if you can get all the desaturations done and you're at C20, you still got to show me the 18 and the 16. Okay?
So it's not like they can work backwards.
You can work backwards. just make sure that you show that your final answer is all in the correct direction. So, like I mentioned, like I showed in class, if I ask for C20 delta pi, make sure the arrows point in the right direction. So then you have C18 and C16. So your final answer reads correctly. You did an elongation here, an elongation there, and a delta phi there. So if I read it, it should say elongate, elongate, delta phi. You did it backwards, but your final answer reads forward. So it's like writing your alphabet backwards. If you write it backwards, you still get the right alphabet, but you're doing it, you're writing it on the page in a different direction. Okay. Everybody okay with those so far? Terpene metabolism, we talked about typical terpenes, isoprene, farnesylgeranyl, cholesterol. These are just longer lipids. They really don't have much functionality. Often they're somewhat desaturated. The main one is that it's cholesterol is the main one of these terpenes we focused on. And of course they're derived from acetyl-CoA acetoacetate, so they're pure lipid derived. The key enzyme is HMG-CoA reductase. It turns HMG-CoA into mevalonate. And this is where our statins inhibit, but it is also the main control point. When we get to regulation, HMG-CoA reductase is the enzyme of regulation.
What is mevalonate? Where does it come from?
Mevalonate is just one of the products. And mevalonate becomes, mevalonate is then turned into the isoprene, and then the isoprenes are added together to make all the variety of terpenes. But it's that one reduction from HMG-CoA to mevalonate that is essentially an irreversible step. That's your committed step. Once you get to mevalonate, you're committed to making some sort of isoprene, whether it be cholesterol or one of these other things.
Thank you.
Yes? Oh, you don't need to know about it. Yeah, that's another one. You don't need to know all of them. I was just demonstrating. I just showed all the steps how to get there, but you don't have to remember. You don't have to learn all those steps. Yeah, is it isopentyl 5-phosphate? There's two of them actually. Now I've completely forgotten.
Just tell us what we need to know.
You don't need to know all that, okay? They're isoprene basic units. And they're derived from acetyl-CoA acetoacetate. HMG-CoA is the main control step. Cholesterol. Now, cholesterol is one of the endpoints of this metabolism. There is no reverse. We do not turn cholesterol into any kind of energetic product. We can make bile salts. We can lose bile salts through our fecal elimination, but we cannot burn cholesterol for energy. So there is no backwards for cholesterol. The also important under cholesterol metabolism are the lipoproteins. There are 5 of them. Chylomicrons, VLDL, IDL, LDL, and HDL. Know what they're carrying, where they come from, where they go to, what their main function is. The VLDLs carry the fat, they deliver most of the fat. LDLs carry most of the cholesterol. Those are the ones that must be completely absorbed. Okay?
Where did the LDLs come from?
Well, they're basically a consequence of VLDLs being turned into IDLs and LDLs. So the liver produces the VLDLs, and as they travel through the bloodstream, they transform into IDLs and LDLs. And the LDL has to be completely absorbed. And if it isn't, it just floats around forever. And the HDL come from the tissue level, and they're produced separately, and they're used to clean up cholesterol and take it back to the liver. So the LDLs take the cholesterol to the cells, the HDL takes it back to the liver. So it completes the cycle of the cholesterol. So far, so good? Okay? Moving on to amino acid metabolism. I talked about deamination and transamination. The cofactor is pyridoxal phosphate, or PLP, derived from vitamin B6. The products are ammonia and a keto acid. But most amino acids are transaminated, so that ammonia goes into glutamine, and glutamine is the means by which we glutamate. Glutamine's different. So most amino acids dump their amine into alpha ketoglutarate to make glutamate, and then glutamate is the only amino acid that is actually truly deaminated, and that ammonia is then turned into urea in the urea cycle. Yes? It makes a keto acid and a new amino acid. So transamination is the moving of the ammonia, the nitrogen group, from one carbon chain to another. It turns, it basically turns an amino acid into a keto acid, and a different keto acid into an amino acid. So there's a play there between keto acids and amino acids where you add and subtract the nitrogen. In transamination, bug. Where's there a bug around? It's 30 degrees outside. But in transamination, what? Deamination is the removal of the nitrogen completely to make ammonia. Most amino acids don't truly deaminate, they just transfer their nitrogen to another keto acid. In most cases, that keto acid is alpha ketoglutarate to make glutamate, which is the only amino acid that is actually truly deaminated. The rest of them transfer it to that, and that's so it's all that nitrogen is shunted into glutamate, and then glutamate has it removed to make urea. Okay? Yeah, well that was alanine. It varies from amino acid to amino acid. So I showed for alanine, we draw it out. This is alanine. That's 3. I'll just write alpha ketoglutarate. The nitrogen is transferred to make now this is pyruvate, because I started with alanine. Now, if I instead started with serine, I would get this. Now this is actually an alpha keto glycerate. So we know that we have glycerate. We know glycerate is glycerate. And we have 2-phosphoglycerate, 3-phosphoglycerate. This is simply an oxidized version of glycerate. So we can reduce this up to this compound. So you basically get the side chain with this keto acid group at the bottom. That's what all amino acids turn into. And then from there, they metabolize further into something else. So some of them, oh, that's the one I'm thinking of. This is an interesting one. Let's see if anybody can. Oh, wait. Oh, yeah, it's, aspartate. Anybody know what this one is? This molecule? Take a wild guess. It's 4 carbons, keto acid. Think of it upside down. It's one of those ones you have to memorize for the test, but it doesn't look the same. So that's why it's so hard. What? Nope. It's no phosphate. So this isn't in glycolysis. It's in TCA.
Oh,
Close. Oxaloacetate. And that comes from aspartate. So you get all these different varieties of keto acids depending on which amino acid you start with. Okay? Actually, transamination can occur in reverse too. So if I wanted to make aspartic acid, I could simply do this. I take some glutamate, my oxaloacetate, mix with my transaminase, it'll transfer the nitrogen onto and make aspartic acid. So that's how the body makes amino acids too. It can take them from an amino acid and put it onto another carbon chain and make a new amino acid. So that's why many of our amino acids are non-essential, because see, like aspartic acid is non-essential, because all I have to do is add a nitrogen to a very common compound to get aspartic acid. Now certain things like lysine, a little harder, a little bit more steps to get to lysine. So lysine would be considered an essential fat amino acid. Glutamate, yep. So there's always alpha ketoglutarate, and glutamate. That's the standard transamination pair. All right, and I mentioned glutamate to you. You don't have to learn the urea cycle. There's like 4 or 5 steps to it. I'm not going to make any of you learn it. It's excessive at this point. There are 2 transport pathways. Most of our cellular tissue uses the glutamine transport. So what it does is it makes an amide on the end of glutamate to turn to glutamine, and then glutamine goes to the liver, which takes that nitrogen off. The muscles are the only ones that use the glucose-alanine cycle. They put all their nitrogen onto alanine, which is then deaminated in the liver back to pyruvate, but then the pyruvate is then converted back into glucose. So the liver is actually, the muscles are sending a pyruvate equivalent, the liver is sending a glucose equivalent back. So in addition to the muscles getting rid of nitrogen, they're also gaining 2 ATPs per pair of pyruvates that they send. So they get more energy back than they send out. So that's the thing the muscles do with the liver. So it's kind of like the Cori cycle, except it's the glucose-alanine cycle. Talked about ketogenic versus glucogenic. Some amino acids can be used to make glucose. So oxaloacetate is part of gluconeogenesis and can be used to turn into PDP and then back through glycolysis to make glucose. So this would be a glucogenic amino acid. Certain amino acids can only be made into ketone bodies, like acetoacetate. Acetoacetate. It's acetoacetate. I thought there was a simple one. I can remember acetoacetate structure. 4 carbons. I don't think it's a simple one. I don't think it's a simple one. We don't acetoacetate. But many amino acids, which are ketogenic, only can be used to make acetyl-CoA and acetoacetate. Those can only be made into ketone bodies. So, and that's the consequence we get metabolically, that sometimes they produce ketone bodies. Yes? No, I'm not going to do that. Yeah, definition-based, or, you know, I'll ask about alpha-ketoglutarate, you know, maybe you have to know glutamate to alpha-ketoglutarate, but not structurally. I'm not going to make anybody draw any structures out of this. You could know that. I mean, I would more think that remembering that the essentials are often ketogenic and the non-essentials are often glucogenic. So that's kind of an important correlation between the two. I was about to get to that right here. But I'm not going to do much I'm not going to do anything structurally. You might have to know the glutamate, alpha-ketoglutarate interplay, how those two go together, because that's basically how we dump all of our nitrogen. The non-essentials tend to be glucogenic. The essentials tend to be ketogenic. What's that? Let me see if I can pull that up again. You don't have to learn that chart, but it's a nice chart to have for reference. I can pull it up here. 16, come on. How many times did I open it? Here we go. I'm so sorry. Some of the essentials can be glucogenic, but all of the non-essentials are also glucogenic, which makes sense because if they're always turned into glucose products, then we can always turn them back into amino acids. Versus the ones that are ketogenic, we can't turn them into glucose, so where are we going to get them from in the first place? So many of them have parts or whole that are completely ketogenic in the essentials. Right. Let's go back to this. Here we go. All right, so that's all I wanted. Yeah. Oh, I'm about to get to that. Yeah, that's all in regulation.
Did you take that double-headed monster and apply it to this ketogenic, glucogenic terms?
No, because that's specifically for glycolysis gluconeogenesis. That's a different topic. Well, I mean, in the grand scheme, yes, the ketone bodies and the starvation are related metabolically, but that two-headed creature of PFK2 and FBPH2 specifically for the controlling glycolysis versus gluconeogenesis. So that's very specific just to that topic. It's not an overall. I mean, if you want to talk insulin and glucagon, we can talk ketone bodies and such, but that particular one is a smaller subtopic.
So you could relate insulin and glucagon to ketogenic?
Yeah. Well, I mean, not to glucogenic and ketogenic, but also the production of those. So the production of the ketone bodies and the glucose tends to be a glucagon favored because you want to produce glucose or produce energy for the body, versus insulin is the breaking down and the use of energy or storage as fat. Okay. All right. We're going to go forward now into regulation. Regulation, this is a big one. This is a big topic. Expect both part 1 and part 2s on this. I gave some sample questions on regulation. I'm also going to ask up and down things, like what's up-regulated, what's down-regulated by insulin, by glucagon. So expect a variety of different questions on regulation. There are 3 levels of regulation: allosteric, signal-based, and genetic. Allosteric are your local controls, which are your non-competitive, both inhibition and activation. That was the feed forward and feed backwards and feedback controls on the pathways. Signal-based were the ones that were responding to external signals. The main consequence is phosphorylation, which turns on or off an enzyme depending on the enzyme. So remember that an on for one enzyme would be off for the opposing enzyme. Remember glycogen synthase versus phosphorylase. Some of the mechanism of the signal transduction We have obviously the receptors, which I didn't put in here, the G proteins, secondary messengers, and the kinase cascade, which results in both diversification and amplification.
What you know about G protein?
What?
What you know about G protein?
First of all, it's the first protein that responds to the signal. It is activated by it activates and so it's not activated by binding GTP. When it is activated, it also binds to GTP to keep it in its activated state, but will slowly degrade that GTP to inactivate itself. So it's basically got this self-installed timer within the G protein that it'll turn on by connection with the signal, turn itself on by binding GTP, but then it hydrolyzes that GTP back to GDP and then inactivates itself. So it's a timed it's a timed signal. The G protein is then further goes to activate things such as that produce secondary messengers, adenylate cyclase, calcium, etc. G proteins are also, don't forget, they are anchored membrane proteins, whereas the receptors are integral membrane proteins. So G proteins, in essence, are essentially globular, but they're anchored to the membrane. Yeah.
Should we have receptors to that list?
You can slip the receptors in there. Yeah, the receptors. They're the ones that actually that are integral proteins that actually receptor the hormone. Yeah, you might want to put that in there. So slip that in right here, but above G proteins. Okay, so that's the signal transduction pathway. Results in phosphorylation. The last level is genetic. This is our transcriptional regulation. Controls the levels or amounts of the proteins. This is a longer term control over metabolism than signal based. All right, so let's go through the examples that we have to remember in glucose metabolisms. And I said cytoplasmic, meaning glycolysis, gluconeogenesis, and glycogen. Typical inhibitors, I went through a few of those. High energy inhibitors will inhibit things that produce energy, so they inhibit glycolysis. They also inhibit glycogen breakdown. Low energy ones do the opposite. And of course, insulin and glucagon have controls, direct control over glycogen synthase and phosphorylase, but it also has control over fructose 2,6-bisphosphate, which is itself an allosteric regulator. So that whole scheme of the 2,6 is made, it then activates PFK and it activates SPPase. Its fate is controlled by that two-headed thing. FBPase2 bound connected to PFK2, which is turned on and off by the insulin glucagon signal. So learn that little setup there. I don't think I'm going to make anybody reproduce it, like draw it. I'm not going to go to that extent. Can be a multiple choice question, or maybe even just a short answer, like a one-sentence explanation. No essays.
Of what? Can you repeat that?
So for the fructose 2,6-bisphosphate, it could either be a multiple choice question, or maybe I'll make it a short answer.
What do you know about it?
It's how it's produced, how it's controlled, what are the enzymes that control it, how they're controlled by insulin glucagon, what it does, that whole scheme that I put together. Kind of important, learn that. All right, so that's for glucose metabolism in cytoplasm. We also talked about allosteric inhibitors of TCA. There aren't really any verified insulin glucagon regulators for that. In lipid metabolisms, the main control point for fatty acids is acetyl-CoA carboxylase. That's the one that turns acetyl-CoA into malonyl-CoA. There are allosteric regulators, and there is a control by the insulin glucagon pathways. Also talked about the hormone-sensitive lipase, which lives at the adipose tissue, how it's affected by glucagon and insulin, and also genetically how insulin and glucagon can up and down regulate different amounts of protein, amounts of the enzymes in both beta oxidation and fatty acid synthesis. In cholesterol metabolism, the main control point there is HMG-CoA reductase. It is controlled signal-based through insulin and glucagon, we'll do that. The genetic control is primarily through steroid regulatory element binding protein, SREBP. That's the protein that hangs out at the ER until it loses its cholesterol, in which at that point it migrates into the nucleus and becomes a transcriptional regulator. So it's dormant until it loses its cholesterol, and it will lose its cholesterol when levels get low, equilibrium. You know, since it binds cholesterol, you drop the levels of binding compound, of binding molecule, it becomes unbound, and that protein then travels to the nucleus. Okay, protein metabolism, I think insulin and glucagon effects. Also talked about growth hormone, how it has similar properties to both insulin and glucagon. And we just did diabetes today. The two types, their relation to insulin levels, which one has high, which one is low, are they sensitive or insensitive to insulin, and the metabolic and physiological consequences. Glucose, ketone bodies, urea production. Physiological, kidneys, and A1C. Any more questions? So you can see that the part twos are not going to be too in-depth here. They're going to be similar to like multiple choice, or maybe a very brief short answer. There's not as you notice, there's not as many practice problems for this one, because it tends to be a little bit more content-based and less activity-based, I would say. Any other questions? Similar length, similar split between multiple choice and short answer. All right? Light looks